The furnace that went cold in seconds. A Steam Stories documentary script, 30 minutes. Chapter 1. The moment the fire died. The pour was routine. Third shift at the Cumberland Iron Works, February 1891. 6 men stationed around furnace number 3, watching 2,000 pounds of iron reach liquefaction. The glow painted their faces orange through leather masks. Heat rippled the air above the crucible, distorting the gaslights mounted on brick columns 20 feet back. Then the color changed. Not gradually, not the way a fire dims when you starve it of fuel. The orange went yellow, then white-blue, then nothing. The roar, that constant, throat-deep rumble of combustion, cut to silence. Complete silence. The kind that makes your ears ring because the sound you've heard for hours just stops existing. One of the pourers, a man named Hewitt, later said the ladle in his hands went from unbearable to merely warm in the span of 3 breaths. The crucible, visible through the charging door, showed no flame, no ember glow, just dark metal and the faint shine of solidifying iron catching the gaslight. The foreman, standing near the blower intake, felt the shift in air pressure. A pull, like the building itself inhaled, then nothing, no updraft from the stack. No heat shimmer. The charging floor, which moments before had been a furnace of reflected thermal energy, became cold enough that men could see their breath. Something had gone profoundly wrong, but there was no explosion, no structural failure, no gas leak, no steam eruption, no collapse. The furnace had simply stopped being a furnace. And in the foundry trade, fire doesn't die without cause. The molten iron in the ladle began to crust at the edges. Hewitt set it down carefully, the way you'd place something fragile, even though it weighed more than he did. The silence persisted. Someone coughed. The sound echoed off the brick ceiling, too loud, wrong. Another man approached the furnace, hand extended toward the charging door. Cold. Not cooling, cold. He stepped back, glanced at the foreman. No one spoke. They'd all worked iron long enough to know what heat retention meant, what thermal mass did. A furnace that size, loaded with coke and iron, didn't lose temperature in seconds. It couldn't. The refractory bricks alone held enough energy to burn skin for hours after shutdown. But the air around the stack was ambient, room temperature, as if the fire had never existed. One of the younger workers started toward the base of the furnace, maybe thinking he'd find a crack, a breach, something to explain it. The foreman stopped him with a hand, shook his head. You don't approach a silent furnace, not until you understand why it's silent. Behind them in furnace number 2, the roar continued. Normal, constant. The contrast made the silence worse. Someone finally said it. The fire's out. Not banked, not smoldering, out. The shift supervisor arrived within minutes, called from the offices by a runner. He stood at the base of furnace 3, one hand on the brickwork, feeling for residual heat. There was none. He walked the perimeter, checked the tires, the air injection ports near the bottom, felt the blast pipe. Cool. The blower system, a massive leather and iron mechanism driven by steam, was still running. Air was still being fed, but it was passing through a dead chamber. He ordered the charging door opened. 2 men levered it up, the iron hinges scraping. Normally, opening that door meant a blast of heat, a wave of combustion air seeking escape. This time, nothing. Just a draft of cold air flowing inward into the furnace. Backward. Inside, the coke bed sat intact. No collapse. No voids. The fuel was arranged exactly as it should be, stratified layers supporting the charge above. But it was ash cold. The iron that had been molten minutes ago was now a frozen mass, mid-drip, solidified in the act of liquefying. Rivulets of metal stopped in place, sculptures of interrupted process. The supervisor stepped back, told everyone to stay clear. Then he did what any man in his position would do. He started looking for sabotage. Damp fuel was the first theory. Someone whispered it and it spread. Maybe a water line had leaked into the coke storage. Maybe someone had deliberately sabotaged the charge, but the coke bunkers were dry. The fuel staged for the next load showed no moisture, no contamination, and even wet fuel wouldn't explain the speed. Damp coke smolders. It smokes. It produces incomplete combustion, carbon monoxide, visible signs. This furnace had simply stopped burning. The blacksmiths were called in, men who understood draft and airflow the way sailors understood wind. They tested the flue, dropped weighted cords down the stack to check for blockages. Nothing. The interior was clear, the brickwork intact. They lit all soaked rags and held them near the charging door, watching the smoke. It rose, slowly, then stopped. Hung in the air. No draw, no suction from the stack. The chimney wasn't pulling. But chimneys don't stop pulling unless something forces them to stop. One of the blacksmiths, an older man with scar tissue on his forearms from decades of forge work, crouched near the base and put his ear to the brickwork. Listened. Then he stood, looked at the supervisor and said, "There's no draft because there's no heat. And there's no heat because something killed it faster than physics should allow." The foundry floor went quiet again. The implications settled. Furnaces don't just extinguish, not modern blast furnaces, not charged, active operational systems running at temperature. You can starve them of air and they'll smolder for hours. You can flood them with water and they'll crack, explode, turn into shrapnel. But you can't make them go cold in seconds without catastrophic force. Yet here it was, cold, silent, intact. By midnight, rumors were moving through the night shift. Some said it was gas, an invisible pocket of something that displaced the oxygen. Others said the fuel had been poisoned, treated with something that killed combustion. A few of the more superstitious workers muttered about bad air, about mines and tunnels where men dropped dead without warning. But the engineers weren't talking about superstition. They were talking about pressure. Morning brought the technical teams. Furnace engineers from the main office, men with blueprints and instruments, calipers and thermocouples. They crawled over every inch of Furnace 3, documenting, measuring, testing. The structure itself was sound. No cracks in the stack. No breaches in the firebox. The tires were clear, the blast system functional. The coke was examined under magnification. Pure, high-grade fuel, no adulterants. The foreman still suspected sabotage. It was the only explanation that allowed for intent, for control. Accidents were predictable. Materials failed in predictable ways. But this wasn't material failure. This was something precise, something that had bypassed every safety mechanism, every thermal buffer, and extinguished combustion without trace. He interviewed the shift workers individually, asked about grudges, about disgruntled employees, about anyone who'd been near the fuel stores or the furnace itself before the incident. Nothing. The crew had been stable for months. No new hires. No recent terminations. And even if someone had wanted to sabotage the operation, how would they do it? You can't carry enough water to quench a blast furnace unnoticed. You can't introduce a chemical agent that leaves no residue. You can't simply wish fire out of existence. The engineers moved to the chimney. 70 feet of brick and iron tapered, designed to create draft through convection. Hot gases rise, cold air rushes in to replace them, and the cycle sustains combustion. It's thermodynamics at its simplest. But when they tested the draft, using smoke charges and pressure gauges mounted at intervals up the stack, they found something strange. The airflow was correct, directionally, mathematically correct. Air was entering at the base, rising through the stack, exiting at the top. But the velocity was wrong, too slow, as if the chimney were pulling against resistance, fighting something. One of the engineers, a man named Drummond, had worked on mine ventilation systems. He recognized the pattern, described it as a pressure differential problem, something you saw in deep shafts when surface air temperature inverted. Cold air is denser than hot air. If cold air sits above a heat source, it resists displacement. The draft weakens. In extreme cases, it reverses. But blast furnaces don't depend on external air temperature. They create their own convection. The heat inside is so intense that outside conditions become irrelevant. A furnace will draft in a blizzard, in dead calm, in summer heat. That's the design. Unless something was overriding the design. Drummond ordered the blower system shut down, wanted to test natural draft, see if the chimney would pull on its own. They sealed the tires, lit a small fire in the base and waited. The smoke rose, slowly, then stopped, hovered, then, just for a moment, descended, reversed, flowed back down into the firebox. The engineers looked at each other. That wasn't supposed to be possible. They checked the wind outside. Calm, no gusts, no weather front. The barometric pressure was stable. There was no external force pushing air down the chimney. But something was. Something inside the system, inside the infrastructure of the foundry itself, was creating a counterpressure strong enough to reverse convection. Drummond walked the perimeter again, this time looking up at the roofline, at the other stacks. Cumberland Iron Works had 6 blast furnaces, 6 chimneys, all of them terminating at roughly the same height, all of them exhausting into the same airspace above the building. And all of them, except number 3, were running. Air moves in predictable ways until it doesn't. Drummond had seen it in mines, how a single ventilation shaft could create eddies and pressure zones that defied intuition. How adding more airflow sometimes made things worse, because air doesn't just flow, it fights. It competes for space, for pressure, for equilibrium. In a foundry with multiple furnaces, you're not just managing combustion, you're managing atmosphere. 6 chimneys, all exhausting hot gases, all creating updrafts, all pulling air from the same foundry floor. And when they're all running in parallel, they interact. Stack effects compound. Pressure zones form. Air doesn't just rise, it channels, it accelerates, it finds paths of least resistance. Furnace 3's chimney was positioned between furnaces 2 and 4. Both of those were operational during the incident. Both were pulling hard, creating strong updrafts. Drummond stood at the base of number 3 and felt the air movement. Lateral, horizontal. Air was being pulled sideways toward the active stacks before it could rise. But that still didn't explain the cold. Weak draft might slow combustion, might make a furnace inefficient. It wouldn't kill it instantly. He went inside the stack, had himself lowered on a rope with a lantern, checking the interior brickwork foot by foot. At 40 feet up he found it. A section of the chimney lining had separated from the outer wall. Not collapsed, separated. A gap, maybe 6 inches wide, running vertically for about 12 feet. The inner liner had pulled away from the structure, creating a cavity. A cavity that was open to the exterior. Cold outside air was entering through that gap, flowing into the chimney through the crack, mixing with the exhaust gases, cooling them, increasing their density. The hotter the furnace burned, the more draft it created, the more cold air it pulled through that breach. A feedback loop. The furnace was drafting its own extinguishment. But even that wasn't the full answer, because cold air mixing with exhaust should still allow combustion. Inefficient, smoky, incomplete combustion, but not instant extinguishment. Drummond climbed higher. Near the top of the stack where the chimney narrowed, he found the second problem. The cap. The iron cap that covered the top of the chimney, designed to prevent rain intrusion, had been modified, fitted with adjustable shutters meant to control draft. Someone had installed them months ago during an efficiency initiative. The shutters on Furnace 3 were partially closed. Closed just enough to create a Venturi effect, to accelerate airflow through a restricted opening, dropping the pressure, pulling harder. Normally, that would increase draft. But combined with the interior breach, the cold air entering at 40 feet, it created a pressure trap. Hot air accelerated toward the top, met resistance from the shutters, couldn't escape fast enough, and backed up. Meanwhile, cold air continued pouring in through the gap, creating a descending column of dense air that fought the rising exhaust. The result was a stall, a pressure inversion. The stack stopped pulling, and when the stack stopped pulling, the furnace stopped breathing. But it still didn't explain the speed, didn't explain how the fire went from full combustion to dead cold in seconds. That answer came from the steam system. Cumberland Iron Works used steam for everything. Blowers, hammers, hoists, pumps. A network of pipes ran under the foundry floor, through the walls, along the ceiling. And one of those pipes ran directly behind Furnace 3, feeding the blast blower. On the night of the incident, a pressure relief valve had opened. Routine, automatic, designed to vent excess steam to prevent overpressure. but the vent location was wrong. The steam exhausted into a service corridor that connected to the base of Furnace 3's chimney. And when that valve opened, it released a massive pulse of steam, superheated, high-pressure vapor, directly into the draft path. Steam is heavier than air when it condenses, and it condenses rapidly when it hits cold surfaces. The steam pulse entered the chimney, met the descending column of cold air from the breach, and condensed instantly. Turned into water droplets, into mist, into a thermal shock wave that dropped the temperature inside the stack by hundreds of degrees in seconds. The draft didn't just weaken, it reversed. Cold air poured down the chimney into the furnace, smothering the combustion zone. Oxygen was displaced by water vapor and cooled exhaust gases. The fire didn't burn out, it was suffocated, drowned in cold air. And because the refractory bricks were already compromised by the weak draft, already losing heat to the infiltrating cold air, they had no thermal mass left to resist. The furnace went cold because the entire system, the chimney, the brickwork, the air supply, simultaneously failed. It wasn't sabotage, it was resonance, a perfect, catastrophic alignment of engineering. They reconstructed it piece by piece, using testimony, temperature records, and barometric logs. The timeline looked like this. 8:47 p.m., Furnace 3 at full operation, pouring molten iron. Interior temperature approximately 2,800 degrees Fahrenheit. Draft strong, combustion stable. 8:48 p.m., steam relief valve opens in the corridor adjacent to the chimney base. Pressure vented, 180 psi. Duration, 4 seconds. 8:48, 15 p.m., steam enters chimney through service access point. Begins condensing on contact with cold air from the interior breach. 8:48, 30 p.m., pressure inversion detected. Hot exhaust gases stall at the 40-foot level, unable to overcome the descending column of condensed steam and cold air. 8:48, 45 p.m., draft reversal. Cold air begins flowing down the chimney into the furnace. Workers on the floor report a sudden pull of air toward the charging door, then stillness. 8:49 p.m., combustion zone oxygen depleted. Fire extinguished. Interior temperature dropping at approximately 200 degrees per second. 8:50 p.m., molten iron in the crucible begins solidifying. Foreman approaches furnace and finds it cold to the touch. 4 minutes, from full combustion to frozen metal in 4 minutes. But the perceptible event, the moment the fire died, happened in less than 30 seconds. The workers described it as wind, not a draft, not airflow wind. A rushing sound like a storm, followed by absolute silence. One man said it felt like standing too close to a steam whistle when it vents, that sudden pressure change that makes your ears pop. Except it wasn't sound. It was the absence of sound. The removal of the constant background roar they'd stopped consciously hearing. Hewitt, the pourer, said the heat vanished so quickly he thought he'd been struck by something. Thought maybe he'd passed out for a moment, lost time. Because heat doesn't just disappear. Your body doesn't go from burning to comfortable in seconds. But it had. The radiant energy, the infrared barrage that had been cooking his face through the leather mask, just stopped. Like someone had closed a door between him and the furnace. Another worker, stationed near the blast pipes, reported feeling the air reverse. A pull, then a push, then nothing. He'd instinctively stepped back, away from the furnace, before he consciously understood something was wrong. Said it was like the building had exhaled. The night foreman's account was the most detailed. He'd been watching the pressure gauge on the blast system, making sure the air supply stayed consistent. Saw the needle drop, not gradually, but in a single swing from 12 psi to 3 psi. Then back up, then down again, oscillating. He'd started toward the furnace, thinking there was a blockage, when he felt the temperature drop. Described it as stepping from summer into winter in the span of 3 paces. By the time the shift supervisor arrived, the furnace was already below 200 degrees. The brickwork, which should have stayed hot enough to burn skin for hours, was safe to touch. The engineers would later estimate that the thermal mass of the furnace, Millions of BTUs of stored heat energy had been stripped away at a rate equivalent to dumping the entire structure in ice water. But there was no water, no coolant, just air, cold air, moving in the wrong direction, carrying heat away faster than the combustion could replace it. It was, one engineer noted, the most efficient furnace shutdown ever recorded. If it had been intentional, it would have been brilliant. The formal inquiry took 6 weeks. Drummond led the team, assisted by 2 structural engineers and a thermodynamics specialist from the university. They documented everything: the chimney breach, the shutter configuration, the steam vent location, the pressure logs, the fuel composition, the weather conditions. Built a scale model of the furnace and the surrounding airspace. Ran simulations using smoke and airflow mapping. The breach in the chimney lining was the primary fault. It had likely existed for months, possibly since the last major refit. The inner bricks had expanded and contracted through thermal cycling, and the mortar had failed. The gap had started small, then widened over time as cold air infiltration eroded the edges. By the night of the incident, the opening was large enough to admit significant airflow, enough to cool the exhaust gases, enough to weaken the draft, but not enough to extinguish the furnace under normal conditions. The shutters were the second fault. Installed as part of a draft optimization project, they'd been set to restrict airflow by approximately 30%. The theory was sound: control the exhaust velocity, reduce heat loss, improve fuel efficiency. But the calculations had been done assuming an intact chimney. With the breach at 40 feet, the restricted top created a pressure trap. Hot gases couldn't escape fast enough, cold air couldn't be expelled, and the system reached a critical point where adding more heat actually made things worse. The steam vent was the trigger. Positioned badly, exhausting into a space that connected to the chimney base, it had introduced a massive thermal disruption at exactly the wrong moment. The steam pulse didn't need to be sustained. 4 seconds was enough. It condensed, created a dense column of cool, moist air, and tipped the pressure balance past the point of recovery. But the real insight came from understanding the interaction between all 6 furnaces. Cumberland Iron Works had designed its facility for efficiency, clustering the furnaces close together, routing steam and blast systems through shared infrastructure. The chimneys terminated at the same height, exhausting into a common airspace. Under normal conditions, this was fine. The hot exhaust from each furnace rose independently, dispersed into the atmosphere, and caused no interference. But when one furnace experienced a draft problem, the others amplified it. Furnaces 2 and 4, running at full capacity, created strong updrafts that pulled air laterally across the foundry floor. That air had to come from somewhere. It came from Furnace 3's charging area, creating a cross-draft that disrupted the already weak chimney draw. The more Furnace 3 struggled, the more air the adjacent furnaces stole, creating a feedback loop. Drummond called it draft competition. In modern terms, it's a pressure interference pattern. Multiple sources trying to pull from the same supply, creating zones of negative pressure, eddies, dead spots. In a ventilation system, it causes inefficiency. In a blast furnace array, it can cause total failure. The investigation concluded with 3 findings. 1. The chimney breach had compromised the thermal efficiency of Furnace 3 for months. Fuel consumption records showed a gradual increase, compensating for heat loss. No one had noticed because the furnace still operated within acceptable parameters. 2. The shutters had been set incorrectly. The engineer who installed them had used calculations based on theoretical chimney performance, not actual measured draft. The restriction was too severe for the real-world conditions. 3. The steam vent required relocation. Exhausting high-pressure vapor into a space connected to furnace draft paths was a design flaw. It had likely caused minor disruptions before, brief fluctuations that corrected themselves. But combined with the other faults, it became catastrophic. The furnace was repaired, the chimney relined, the shutters removed entirely, the steam vent rerouted to an external exhaust. and protocols were implemented to monitor draft pressure across all furnaces simultaneously, watching for the interference patterns that indicated one furnace was stealing air from another. Furnace 3 was returned to service in April 1891. Ran without incident for another 40 years before being decommissioned during the Depression. But the engineers who worked on the investigation never forgot it, because it demonstrated something most people don't think about. Industrial systems don't exist in isolation. They're ecosystems. And in an ecosystem, everything affects everything else. The story of Furnace 3 became a case study. Not famous, not widely known outside specialist circles, but referenced in engineering texts on thermodynamics and industrial ventilation. It appears in a 1903 manual on blast furnace design in a section on draft management. Shows up again in a 1920s paper on pressure dynamics in multi-stack facilities. Gets mentioned in OSHA documentation on industrial atmospheric control. Because what happened at Cumberland wasn't unique. It was just dramatic enough and well documented enough to become a teaching tool. Industrial facilities are full of invisible forces. Pressure, temperature, airflow. They move through buildings, through equipment, through infrastructure, shaping how systems behave. Most of the time, we don't think about them. We see the machinery, the metal, the physical components. We forget that between the solid parts, there's air. And air has weight, has momentum, has preferences about where it wants to go. Early blast furnaces were built by men who understood fire and metal, who'd spent lifetimes at forges and foundries, who knew heat the way sailors knew wind. But the transition to industrial scale, to multiple furnaces, to integrated steam systems, to optimized layouts, introduced complexities that intuition couldn't predict. You couldn't feel a pressure differential, couldn't see a draft reversal coming. Couldn't know that closing a shutter on one chimney would affect combustion in a furnace 50 feet away. They had to learn it through failure, through furnaces that went cold, through explosions, through gas pockets, through all the ways that invisible forces could assert themselves. The men who worked at Cumberland knew their equipment, knew the sound of healthy combustion, the feel of good draft, the color of clean flame, but they didn't know the building was fighting itself. Didn't know that every time they started a furnace, they were changing the pressure map of the entire facility. Didn't know that steam venting in one corridor could extinguish fire in another. Nobody did, not until it happened. That's the lesson, if there is one. Industrial systems are built from more than metal and brick. They're built from air and heat and pressure, from forces that exist in the gaps between components. And those forces follow laws that don't care about design intent or engineering confidence. You can build a perfect furnace with ideal geometry and precise tolerances and the finest materials. But if you put it in a building with 5 other furnaces, with steam systems and ventilation networks and chimneys that exhaust into the same airspace, you've created something more complex than the sum of its parts. You've created an atmosphere, an ecosystem, a space where invisible forces collide, where pressure and temperature and airflow compete for dominance, where small faults can cascade into total failure. And sometimes, on the wrong night, with the wrong combination of circumstances, that ecosystem turns hostile. The fire goes out, the heat disappears, the roar becomes silence. And men stand in the cold, staring at a furnace that shouldn't be possible, trying to understand what invisible thing just reached out and killed their fire in seconds. That's the truth of early industry. It wasn't just about building machines. It was about learning to see the invisible, learning that the empty space between components wasn't empty at all. It was full of forces, and those forces had rules. You just had to figure out what they were before they killed someone.